For centuries, humans have been fascinated by the microscopic world. We have long known that there are things too small to be seen with the naked eye. But it wasn't until the invention of the microscope that we could finally start to explore this hidden realm. Optical microscopes, which use light to magnify objects, have been around for centuries. However, even the most powerful optical microscopes are limited by the wavelength of light. This means that they can only magnify objects up to a certain point. In the early 20th century, a new type of microscope was invented, the electron microscope. Electron microscopes use a beam of electrons instead of light to illuminate objects. Because electrons have a much shorter wavelength than light, electron microscopes can achieve much higher magnifications than optical microscopes. Electron microscopes have revolutionized our understanding of the world. They have allowed us to see things that were once thought to be impossible to see, such as viruses, atoms, and even the structure of DNA. The transmission electron microscope, or TEM, is a type of electron microscope that transmits a beam of electrons through a very thin specimen. The electrons interact with the specimen and are then detected to form an image. TEMs are very powerful microscopes and can achieve magnifications of up to 10 million times. This means that they can be used to see objects that are just a few atoms in size. Here's how a TEM works. First, a beam of electrons is generated by an electron gun at the top of the microscope. The electron beam is then focused by a series of lenses. Next, the focused beam is transmitted through the specimen. The electrons that pass through the specimen are detected by a detector below the specimen. Finally, the detector converts the electrons into a signal that can be used to create an image. TEMs are used in a wide variety of fields, including materials science, biology, and medicine. For example, TEMs are used to study the structure of materials, the function of cells, and the causes of diseases. The scanning electron microscope, or SEM, is another type of electron microscope. Unlike the TEM, which transmits electrons through a specimen, the SEM scans a focused beam of electrons across the surface of a specimen. As the electron beam scans the surface of the specimen, it interacts with the atoms in the specimen. This interaction produces a variety of signals, including secondary electrons, backscattered electrons, and X-rays. These signals are then detected by detectors and used to create an image of the surface of the specimen. SEM images are typically three-dimensional and show the surface topography of the specimen in great detail. SEMs are used in a wide variety of fields, including materials, science, biology, and forensics. For example, SEMs are used to study the fracture surfaces of materials, the morphology of cells, and the composition of gunshot residue. The reflection electron microscope, or REM, is a type of electron microscope that uses an electron beam to probe the structure of surfaces. Like TEM and SEM, REM relies on the interaction of electrons with matter but captures the reflected electrons. In EREM, the electron beam is incident on the surface at a grazing angle, and the reflected electrons are used to form an image. This technique is particularly sensitive to the surface morphology and can reveal information about the atomic arrangement of the topmost layers of a material. EREM is a powerful tool for studying surface phenomena such as crystal growth, surface reconstruction, and the formation of thin films. It is also used in the study of catalysts, semiconductors, and other materials where surface properties are critical. Comparing the microscopic titans TEM versus SEM versus REM. While TEM, SEM, and REM all employ electrons to investigate materials, they each offer unique capabilities and are suited for specific applications. Here's a comparison: TEM strengths high-resolution imaging of internal structures capable of atomic scale resolution. Limitations: requires very thin samples. Complex sample preparation primarily provides two-dimensional images. SEM strengths: versatile, can image a wide range of sample sizes and types, provides detailed surface topography. Limitations: lower resolution compared to TEM, primarily for surface imaging. REM strengths: extremely sensitive to surface features, can reveal atomic arrangements on surfaces. Limitations: requires very flat and clean samples, limited to surface analysis. The choice of instrument depends on the specific research question and the nature of the sample being investigated. Electron microscopes have revolutionized many fields of science and technology. They have allowed us to see the world in a whole new way and have led to countless discoveries. In materials science, electron microscopes are used to study the structure and properties of materials at the nanoscale. This information is used to develop new materials with improved properties such as strength, durability, and conductivity. In biology, electron microscopes are used to study the structure and function of cells and tissues. This information is used to understand how cells work and to develop new treatments for diseases. In medicine, electron microscopes are used to diagnose diseases, develop new drugs, and study the effects of environmental toxins on human health. Electron microscopy is a constantly evolving field. New technologies and techniques are constantly being developed, which are leading to even more powerful and versatile electron microscopes. One promising area of research is the development of aberration-corrected electron microscopes. These microscopes use sophisticated lenses to correct for aberrations, which are distortions that can occur in electron beams. Aberration-corrected electron microscopes can achieve even higher resolutions than traditional electron microscopes. Another area of research is the development of in situ electron microscopy. This technique allows scientists to study materials and processes in real time under realistic conditions. In situ electron microscopy is providing new insights into a wide range of phenomena, such as the growth of crystals, the behavior of catalysts, and the function of cells. From the intricate workings of cells to the atomic structure of advanced materials, electron microscopes have allowed us to unravel the tapestry of the universe at its most fundamental level. They have been instrumental in groundbreaking discoveries, including the identification of viruses, the development of new drugs, and the advancement of nanotechnology. As technology continues to advance, we can expect even more exciting discoveries and applications of electron microscopy in the future. The journey into the infinitesimal continues, driven by the insatiable human curiosity to understand the building blocks of our world. Electron microscopes serve as our eyes into this hidden realm, revealing the secrets that have long eluded our perception. The invention of the electron microscope marked a pivotal moment in the history of science. It provided humanity with a powerful tool to explore the world beyond the limits of human vision. From unraveling the complexities of biological systems to designing novel materials at the atomic scale, electron microscopy has revolutionized countless fields. As technology continues to advance, we can anticipate even more sophisticated electron microscopes capable of pushing the boundaries of our knowledge further. The enduring legacy of electron microscopy lies not just in the discoveries it has enabled, but also in its capacity to inspire future generations of scientists and engineers to delve deeper into the mysteries of the universe.